Good morning, or good afternoon, or good evening, depending where in the world you are. Welcome back to our lecture series on the basics of macromolecular crystallography. Let's see. Today, Gianluca Santoni from ESRF is going to speak to us. Oops, sorry. He's a serial data specialist at the European Synchrotron in Grenoble. He did his PhD in drug development based on structures. He then moved on to work at the Beamline at ESRF, where he also developed CC Cluster, which is a dedicated software to find out how similar different crystals are, something which is immensely important to anything from fragment screens to serial crystallography. He then went on to become the scientific coordinator of iSpy-B, which is a software that is used at most European synchrotrons to hold and administer the data that are used for synchrotrons. And he is truly an expert in crystallography in my generation. So I'm very much looking forward to his lecture today, and I hope you will enjoy it too.
Thank you, Andrea, for the nice introduction. So let me just start sharing my screen. I need to move a few windows around here. Zoom is not optimized for Linux. So desktop here, share, voila, and Shift Control P. Voila. So today I will be giving you an introduction on how a diffraction experiment is thought and built. And obviously this is by no way meant to be a complete course on diffraction or on crystallography or whatever, but it's just my take on how you can learn why we do certain things when we collect data at the Beamline. First and foremost, it's very nice to give this talk here today. Sorry, I forgot to move this away. It will probably be better. Because it's a shared day between the University of Würzburg, where William Röntgen exactly 125 years ago discovered the X-rays, and Grenoble, where 200 years ago exactly, Joseph Fourier wrote his essay on the heat transfer, which, between other things, contained the definition of what we call today the Fourier transform, which is the basis of one of the basic tools for crystallographer to go from diffraction images that we will see today how we collect to get the electron density map. That will be obviously the object of the following lectures. So today the outline will be the following. We will start by quick definition of what to me is structural biology. And then I will introduce the Bragg's law, which is the main tool, the main definition for crystallographers. We'll then go and analyze what's the theory behind the diffraction experiment and how the diffraction experiment can be translated from the theory to the Beamline setup. Then this is based mostly on the geometry of the experiment and on the idea that the crystal will be, that it will be possible to collect forever from the crystal. But actually we will see that this is not true because of radiation damage, which is a very big deal, especially in protein crystallography, not so much in material science. Due to the different techniques that we use to avoid radiation damage, we will see that there are different ways to handle crystals, either at room temperature or at cryo temperature. And we will see what are the main tools to go from the home lab to the Beamline. I will explain you then what's the basic setup of the Beamline. And finally, I will briefly talk about how to determine the proper strategy to collect the optimal data from your crystal. So, first question, structural biology asks the question, what does a protein look like? We can answer with different level of detail. At first, we can look at the surface of the protein. So this is just a generic protein that I took from the PDB and just showing the surface. We can look at the secondary structure elements. If we go a bit higher resolution than before, we will see that we can define the secondary structure elements inside the surface of the protein. Or we can maybe want to look at side chains. This is particularly important if you want, for example, to do structure-based drug design. It's important to know where the side chains of each amino acids are looking at. What tools do we have to look at atomic resolution at this side chain? So here in this representation, for those of you who are not familiar with, and I hope you see my mouse, each point in these sticks represent one single atom, which means to see the individual atoms, we need to achieve a certain level of resolution. So first question, how big is an atom? And first and foremost, to look at small objects, we obviously can use a microscope. But yeah, how small is the object we want to look? An hydrogen atoms, to start with, its ground state has a radius of 0.5 angstrom, which is 5×10 to the minus 11 meters. So it's quite small. And more relevant probably for protein structure is the carbon-oxygen bond, which has a theoretical length of 1.43 angstrom. Now, why don't we use optical methods? First, we need to choose which wavelength to use. The classical optics tells us that the maximum resolution D that we can distinguish is determined by lambda, the wavelength, divided by 2 multiplied by the numerical aperture of the object. The numerical aperture is in general a number which is bigger than 1.3 probably for an ideal optical system. So we need about 2 angstrom resolution to see the actual atoms. 2 angstrom resolution in the electromagnetic spectrum correspond to the X-rays domain. So here, obviously, in this picture of the electromagnetic spectrum we put out was the visible light. First, we can see why we cannot use visible light to observe proteins, because if we divide roughly by 2 the 400 nanometer, we will get 200 nanometers, which, just to give you an idea, is twice the size of the coronavirus. So X-rays in general are a domain which are classified of radiation which has a wavelength between roughly 10 nanometers and 0.1 angstrom. It's quite a wide domain, but all the synchrotrons in general are built so that we are optimized to produce X-rays around 1 angstrom wavelength, which is the typical order of magnitude of chemical bonds as we have seen. Then, why don't we do X-ray microscopy? That will be nice. Problem are multiple. First is that X-ray optics have very poor performance, which means the microscope will have a very bad numerical aperture at first. And that second and most important, they will be big because we cannot focus and defocus on a very narrow space. So we will need a lot of propagation space to get a higher increase in size of the object we are observing. More specific to biological samples, they give very low contrast. I found funny this picture, so forgot to show at the beginning, but the first X-ray picture that has been taken in history is actually the hand of the wife of Mr. Röntgen. And 125 years later, we still get the same kind of picture. This is famous skateboarder Tony Hawk, who just last week broke his hand. And you see why X-rays are very useful, because we can see through and see the bones. But you can also see that the biological sample that we are interested in, which is the flesh around the bones, it's actually just a slight shade. So it's very difficult to observe it with the X-rays. So we need a different approach. Luckily enough, X-rays are waves, so we can get a bit creative with our approach, and we can use, for example, the interference. The phenomenon of interference works like this. So we have 2 waves that propagate in the same space. At each point, the waves can be either summed. In this case, we get a higher value, which is the sum of the 2. Or we can get destructive interference. In the blue zones, we see that the waves sum so that we get a 0 value, and we see peaks going around. Why is this important? Because we can generate interference using crystals. If you remember from Andrea's talk the other week, a crystal is what? Is an oriented ensemble of objects which have a repetition in space. For example, if we take the same protein from before, we repeat it in space. Normally they touch. This is just to show you the basic idea of how the protein should be arranged in space. We get a crystal. Why is this important? Because when we shine light to a crystal, now this is a simplified view, and I replace the protein with some dots just to make it easier, but we can generate interference. And why is this important? Because if we have an incident wavelength lambda hitting the crystal planes, each plane will reflect the light. at some moment we will get constructive interference when the projection of, when the path between these two waves is a multiple of the wavelength. Since this path is twice the distance between the two planes multiplied by the sinus of the incidence angle, we get this law, which is most known as the Bragg law, which gives us the conditions when we will get a constructive interference from crystal planes. So you see, we can get a direct information of the distance between the crystalline plane that define a particular diffraction spot by simply knowing the incidence angle and so the exit angle from the crystal. Another way that we can use to define the diffraction condition is by using the Lawes equation. What do they tell us? They tell us that the scalar product between the unit cell parameter of the crystal and the diffracted vector S must satisfy, something has disappeared, must be multiple, must be satisfied for each integer h, k, and l, which means we can get only diffraction at discrete position and we can get it in all the possible direction in space. Problem with this is that, there's not a problem, but we make the assumption here that the crystal is an ideal infinite object. We will see later how these affect the whole representation, of course. The lattice of all the possible diffracted vector here on the left is what we call the reciprocal lattice. It is defined by vector relationships between the unit cell parameters. And all the HKL vectors in the reciprocal space are multiple integers of A star, B star, and C star. With this definition, we can therefore build a space, which is what we call the reciprocal space, where all the possible diffraction vectors exist. Why is this important? Because it gives us a way to conveniently represent a diffraction experiment. So the basics of our experiment is this: we get a crystal, is this black block here, and we shine X-rays on it. Now we can draw the reciprocal space, is this series of dots, and we represent our wavelength starting from the equation before. It's just a translation of that, like a sphere, in this case a circle because we are in 2 dimensions, of radius 1 over lambda. And this construction is useful because the Lawes equation are satisfied every time the sphere meets the reciprocal space. Each time we get a crossing between the two, we get a diffraction vector. We will see later how this helps us building the diffraction experiment. In real case, the situation is a bit different as before. First, reciprocal lattice points are not points, but they are rather spots with some dimensions. This is due to properties of the crystals, like a certain difference between the different unit cells, what we can include in the mosaicity value, the thermal agitation of the spots, and the anisotropy that we can observe in some crystalline planes. And also the Ewald sphere as a thickness is not as perfectly thin sphere, but it has a certain thickness because X-ray radiation is not monochromatic when we perform the experiment. In general, at synchrotron beamlines, delta lambda over lambda, which is our energy spread around the nominal energy, is 0.1%. When we do electron diffraction, just to give you an idea, the spread is about 1 over 300,000. So the Ewald sphere is way thinner than that. And when we do what we call Lawes crystallography, where we increase the thickness by using what the so-called pink beam containing more reflection, we go up to 3% of energy spread. At this point, to collect diffraction from the crystal, we simply rotate the crystal. This will rotate also the reciprocal space, and new reflection will cross the Ewald sphere. What does this mean at the beamline? So, as I said before, you can see here, every time the Ewald sphere crosses a reciprocal lattice point, we can see that a diffraction vector is generated. The diffraction obviously propagates in space. Now we need to intercept this with a detector in order to collect some data. If we put the detector here, we see that at a certain distance, we see that some of the diffraction vectors are actually going out. Please, in all this representation, remember that the reciprocal space is actually infinite, and I'm just drawing a part of that for the sake of comprehension of the picture. So the black square represents the detector. We will detect a diffraction spot per vector that intercepts the detector. If we move the detector closer, you see we can intercept more vectors, but those are getting closer to each other, which can be a problem when we have a lot of those, for example, when the unit cell is particularly big. Where exactly to put the detector? So this is a very approximate representation of a diffraction pattern. You can see that from the picture before, our diffraction pattern has actually a circular symmetry. More precisely, diffraction spots come out of a cone from the sample, from the interaction between the beam and the sample. We can choose to put the detector mainly in two positions at the beamline. Either we put the detector so that the corners of the detector intercept the highest resolution possible. Due to the inverse relation between the resolution and the reciprocal lattice vector, the farther from the center we go, the higher the resolution that we are observing. So here you see, for example, on this circle, we are at a certain resolution. We can set the highest resolution at the corner of the detector. The problem with this is that we are, yes, filling the detector with diffraction, but we are also losing some important information here. Those spots are not collected. We can take the opposite approach and say, we put the edges of the detector at the highest resolution, which makes sense. But also in this case, we can have some problem because the first and foremost that you can see is that there is basically a ratio of pi divided by 4 between the part of the detector that is covered with diffraction spots and the part which is blank. This means you are wasting about 15% of our pixels, which is not the best when we are paying so much for a detector. So there's a compromise that needs to be found. There is no right answer to that. In general, we tend to position the detector as this, but there are some cases where things are a bit different, and we will see later why. Now, the goal of our experiment is to collect the whole reciprocal space. This is obviously impossible because the highest resolution we want to collect is at first limited by the radius of the Ewald sphere, or if we go back to our description of classical optics, is simply limited by the incident wavelength. We cannot collect resolution that go to an angle which will be higher than 1 over lambda. So we can collect the whole reciprocal space possible in our conditions. How many reflections we can observe is actually fixed by a few parameters: the unit cell parameter, the possible resolution of the crystal, or the resolution at which we fix the detector, and the space group will determine how many reflections we can observe from this crystal without doing anything. In general, to observe all the reflections, we need to collect 180 degrees, because in this case, we will have all the reflections possible from this particular crystal in the experimental condition defined above will be collected at some point. But we have something which is helpful, and it will be the object of, in more detail, of following lecture, which is that crystals have actually a symmetry that will reduce this value, which means the higher the symmetry of the crystals, the lower rotation we can collect to achieve a complete data set. And what do I call completeness? Actually, now it should be a bit more clear, is the ratio between the number of reflections we actually observe in our experiment and the number of all the possible reflections at each fixed resolution. So this is how a diffraction image looks like. You can see that diffraction goes more or less in circles. This is something I picked randomly from our database of diffraction images, but it's important because it can help us show some parameters of the beamline. First, we can start from the red cross in the middle, which is the center of the beam. The center of the beam is important because since the whole system, the whole processing is to determine at which angle precisely each spot has left the crystal, we need to know precisely where the center beam, where no diffraction and no interaction with the sample happened, has crossed the crystal. Then with trigonometry, we can simply determine the angle by knowing the distance between the center and the particular spot and the distance between the center and the sample. This blank region here is the beam stop. We will see later that most of the X-rays that we send to the detector actually simply cross the sample without doing anything. If this very intense beam would reach the detector, it will burn it very, very quickly. So we put some metal in the middle. Normally it's a tungsten rod. Why tungsten? Because tungsten has one of the highest atomic number possible for metals with which you can actually build something, some object. And so it's a useful metal to produce a beam stop because it will basically stop the whole incident beam. And then the blank region in between all these rectangles represent the blank region of the detectors. This is collected, if I remember correctly, from a Pilatus detector, and the Pilatus is a collection of sub-modules. And this sub-module has its own electronic, but then there are blank regions when we connect the two modules between each other. As I was explaining before, the highest the angle of exit, the farther the diffracted beam will intersect the detector from the center of the detector itself, the highest the resolution. So highest resolution, as you see here, for example, in this image, the detector was set probably, I will guess, at 1.15 angstrom, because the 1.13 circle just goes out by a very small value. And it's very difficult to see here, but there are spots up to 1.15 roughly. So this is one of the cases where the resolution was set at the edge of the detector to collect the most spots possible. And you can see, we will see this later why, but not all the spots looks the same. So if you think about what we present up to now, there is no reason for a spot to be different than the other. They should all, actually we didn't even talk about the intensity, we just talked about angles, wavelength, and geometry, and position of the detector. So why the spots look different? Because for what we know until now, the spots should all look the same. There's a red line that appears and it's not on my screen. I don't know what that means. So I will go very briefly here, but each spot actually has an amplitude that we can call the structure factor. The amplitude is determined by the interaction of the incident beam with all the possible atoms inside the crystal. This is what we can say here. If you assume that the crystal is ideally infinite, this sum becomes an integral, and the structure factor can actually be defined like this. So it's an integral over the volume of the crystal for this specific HKL of the electron density in space of the crystal. What does this mean? This means that the intensity that we observe on the amplitude of the structure factor that determines the amplitude of the wave hitting the detector is actually determined by the electron density of our sample. If we know a bit about mathematics, we can recognize here a definition of the Fourier transform, which means we can go between the amplitudes or the structure factor to the electron density using a Fourier transform. Problem is that, as you see here, there is a complex number in this exponential, which means the structure factor has both a real and an imaginary part. Why is this a problem? Because when we want to do the inverse Fourier transform, we need to know two parameters. We need to know the module of the vector and what we call the phase. The phase is basically the exponent of the complex part. Now, our detector doesn't measure amplitudes, but measures currents. Currents are proportional to the intensity of the incident wave, and the incident wave, the intensity is actually given by the square module of the complex number, or if we define in complex number terms, by the number multiplied by complex conjugate, which means that the complex part is lost when we do the experiment. We will need to retrieve this somehow, but there will be probably more than one lecture about how we can solve this problem, but this is where the problem arises. So we are measuring by measuring the intensity of the wave, but we are really interested in the amplitude of the wave, and there's no way to measure the amplitude experimentally. So we can only go with intensities and then try to guess later what the phase was. Another problem is that not all the reflections are recorded integrally. So if we zoom in the picture before, we have our Ewald sphere with this thickness, we can see that some reflections are not entirely going through the Ewald sphere. This is basically all inside. This just touches by a bit, and this is probably touching or probably not, I would say yes. How do we measure the full reflections? Either we increase the thickness, as I mentioned before. The problem is that by increasing the thickness, we will create problems because we will introduce more and more reflections coming from different angles to the sample, and it will be difficult to determine which wavelength actually give each of the reflections. And so this is another domain of crystallography, which we call again Laue crystallography. This is, for example, how neutron experiments are done. To increase the number of incident neutrons, we accept more wavelength to the sample. This gives problem in treatment afterwards. Or, as I said before, we can rotate the crystal while collecting a picture. In this case, we have a certain exposure. The reflection will go for a certain time through the sphere, and we collect not really a picture of a static picture as I'm showing here, but sort of very slow diffraction movies over a certain rotation angle. Now, how much we rotate per image of this movie? In the past, what we did is actually rotate about 1 degree per image. What happens, you can see in the first square of this picture, this is taken from a paper about the optimal slicing for crystals. If we rotate for 1 degree, we collect, obviously, we have one measurement for one amplitude, for one diffraction spot. Problem is that the rotation is so wide that we can start collecting also second spots. And these actually in the diffraction image will turn out as a single peak, not as multiple peaks. So we'll not distinguish the two between them. First problem. And second problem is that we have one measure per one per quantity, which is not the best way to estimate the experimental error, obviously. So we can do what we call fine slicing here. Just to spoil a bit the conclusion, this is what we usually do at the Beamline because it's a good compromise between having some repetition of measurement over the amplitude, plus being able to do some profile fitting over the profile of the reflection itself, and not collecting too many images. Or we can go super fine slicing, for example, in the last picture, where we collect 4 images per 0.1 degrees. In this case, the experiment obviously we require to collect 4 times more than here, and 40 times more than here in the first case. Can be done, it can slow down the experiment, but in some condition this is important. For example, again, for very big unit cell where the spots are very close, it's important to do a thinner slicing. In general strategy is to collect 0.1 degrees at the Beamline. So now we can collect data. We know everything about diffraction. We know how to measure reflections using the detector. We can decide where to put the detector once we know what is the resolution achievable by our crystal. What we are left with is just to shine X-rays over our crystal. But actually we are missing a big part of the picture, which is understand how the photons interact with atoms. So photons, at least at the energy domain of the X-rays, interact with the electrons around the atoms, which means, which means the higher the atomic number, the higher will be the so-called cross-section or the probability of interaction between the X-rays and the sample. Here we can see this is the cumulative cross-section of photon-atom interaction over a very wide range of energy for both carbon and lead. First thing we can observe is that at any fixed energy, the lead cross energies is about 10 to 20 times bigger. It's obvious because, as I said, the most important value is the atomic number, and the lead has about 12 more, actually exactly 12 times more electrons than carbon. Since proteins are mainly composed by carbon, we can focus a bit more on carbon. So in the domain of X-rays, which is about here, where my mouse is pointing now, we can see we have two main phenomena that happens. One is the coherent scattering, what we call diffraction, is what's important for us. And the other is the absorption, which is this big wave here. Absorption by photoelectric effect, of course. There are other effects that become important at higher energy. As you can see, there's a factor about 20, roughly, between the cross-section for coherent scattering, which gives diffraction, and the photoelectric effect. What does this mean is that, first, as we have seen before, very few electrons, photons interact with the electrons in the crystal. And of those who interact, actually only a few give diffraction, but even more will be absorbed and generate damage inside the crystal. This is the source of what we call radiation damage, which has a lot of symptoms that are being known since the beginning of crystallography. The first and most important is that there is a resolution lost along the data collection. the first image will always be, if the crystal is good enough, obviously, the first image will always be at higher resolution than the last one. Other symptoms include increase in mosaicity, increase in unit cell volume, and increase in Wilson B factor, which we can consider as the thermal agitation of atoms inside the crystal. So what happens inside the crystal? As I said before, there are absorbed photons that will create free radicals inside the crystal that will move around and will cause all sorts of damage to the crystal structure that will generate the kind of problems that we introduced before. How we can avoid radiation damage? This has been a question as old as protein crystallography. There are different strategies. So the first structures collected from protein crystals were done using multiple crystals. It's simple. It was very long to collect image from our crystal. By the time you were done collecting diffraction from the sample was both dehydrated, completely dried, and also damaged by radiation damage. We could also think of preventing crystals from drying out. I will show you different ways of keeping some humidity inside the crystal, which helps with keeping the crystal for a long time inside the beam. We could use scavengers. This is a research that has been ongoing also since the beginning of crystallography, basically. And scavengers are water molecules that will absorb the free radicals before they can actually cause damage. So before they interact with the protein itself. We could cryocool the crystals. This has been the main choice for the last probably 30 years. Or we could use multiple crystals. This is why I put it back, because in the last few years, there was a resurgence of method using multiple crystal, which goes under the generic name of serial crystallography, where instead of trying to preserve your crystal from radiation damage, you just collect the most data possible from one single crystal before it dies due to radiation damage, and then go to an next crystal. Basically, it's exactly what was done in the 60s, but on a larger scale. So we can go back to a few solutions. The first is humidity. How we can keep crystals humid? We know from previous lecture by Andrea that protein crystals contain a lot of water. They can contain something between 20 and 75 to 80% of water. Average on the PDB is extremely close to 50%. They get dry during data collection for two reasons. One, because experimental hatches are in general very dry environment, and two, and most important, because of radiation damage. Preserving humidity has been always known to extend the lifespan of crystals. There are different methods to do this. One, which is the old school mount, as I call it, which is to mount crystalline capillaries. This is how data were collected in the past. We could just fish crystals inside a quartz capillary with some of their matter liquor. So crystal would basically sit inside this tube with this matter liquor. We would shoot X-ray through. We can rotate this tube because the crystal, as you see, is stuck in the middle, so it will rotate with the tube. So we could collect diffraction data from this. A modern variant of that is this kind of caps where we put, here is color fluid, so it's easier to see. We can put some of the mother liquor at top. We fish the crystal here in the tip, and then we close everything, and it creates a sealed environment. But it has the advantages of modern loops, which is we can fish the crystals easier. The third solution is the humidity control device. So we can simply blow humid air during the full data collection on a crystal which has been fished on a standard support. Or we can use cryocooling. Cryocooling, as I said, has been the method of choice for the last 30 years because it's very easy to collect data. And people realize very quickly that a crystal would have a lifespan which is about 100 to 1,000 times longer compared to room temperature when it's cooled down to cryogenic temperatures. By this, I mean the temperature of liquid nitrogen. So roughly, the temperature of liquid nitrogen is obviously 77 degrees Kelvin. What we do then for the experimental setup is that we set everything at 100 Kelvin, corresponding to minus 173 degrees Celsius. At this temperature, free radicals can basically not move, because their Freeman path is reduced by a lot. So the only kind of free radicals that can move around are actually electrons. And so due to this, cryocooled crystal will last longer into the beam. Is everything perfect with cryocooling? Obviously not. A lot of things can go wrong. At first, the bigger is your crystal, the less uniform will the cooling be. And so there's a huge risk of increasing mosaicity. Mosaicity, as we have seen before, is one property of the crystals that gives us an idea both of the spread of the unit cell size, but also of their reciprocal orientation. If the mosaicity is increased, the spots of our diffraction image will look worse, and the achievable resolution in general goes down. Also, crystals contain a lot of water. When we freeze water, water tends to form ice, and ice is very bad because one is a crystal, two, water is formed by oxygen and nitrogen, and oxygen is basically the same atomic number of carbon, which means they diffract more or less with the same power of protein crystals. In this picture here, we can see the direct symptom of this, which is the formation of ice rings. We can see that our protein still diffracts, but we can see superimposed to these rings, which are obviously at very fixed resolution due to the determined by the unit cell of ice, of crystalline ice. Those will create problem at two levels. At first, too much crystal with too much ice will disrupt the crystalline order inside the protein crystal, again destroying the diffraction capabilities of our crystal. In the best case, we just lose some resolution. In some case, the ice will completely disrupt the crystalline order, and we will just be left with ice rings and no protein diffraction at all. How to avoid this? The most common way is to use cryoprotectants. So when we fish our crystals, we put them in some solution which is one, compatible with the mother liquor, and two, that avoids water to freeze. In general, it's some mixture of glycerol or PEG. The problem is that also cryoprotection can affect the achieved resolution because it's a new solvent that we introduce inside our crystal. And so before even we freeze, we can already be disrupting the crystalline order. So it's very important to screen for cryoprotecting conditions before going to the beamline, or to test at least different cryo condition before to send crystals with different cryo condition to the beamline. And the other problem, and this is more of a practical one, is that the crystals must be kept cool at all time, because temperature changes will obviously favorize the appearance of crystalline ice, and this will disrupt obviously the diffraction again. So this is a very long job that starts at home, where we need to fish crystals or harvest crystal, depending on how you prefer to say this. The most common tools used for this is the litho loop or cryo loop. Here is a picture from the catalog from Mitagen. Why are there so many different sizes? You know that protein crystals come in very different sizes, and we cannot choose which size we will get, especially for the first times we are producing those crystals. So we need to have different tools, first to be able to extract the crystals from the drop, from the crystallization drop where they have grown. And then it's also important because when we harvest the crystals, the least solvent we leave around the crystals, the easier it will be to flash cool those crystals, because there will be less volume of material to cool when we plunge them into the liquid nitrogen. So it's important to choose the adapted size. One, again, for the sake of speeding up the cryocooling process. And second, because less solvent around the crystal means that there will be less background on the diffraction images. Obviously, a litho loop is a very small object. This one, the big one, is 300 microns in diameter, so it's very small. To handle them, in general, we put them on a base. This is a magnetic base that can be then put on the beamline, either manually or by a robot, as we will see later. Once those pins are, the crystal are fished inside the pin, they need to travel to the beamline. So we use what we call packs. Here I'm showing two examples. At top is a spine pack, and at the bottom it's a unipack. There are two different standards that are today available at different light sources. Advantages and disadvantages. Spine packs are easier for the scientists. There's a lot of space to maneuver around. Even when they are plunged in liquid nitrogen, it's very easy to see each position. But they are less compact. Unipacks, on the other hand, are more compact. You see, they have the same exact diameter, but we can put 16 crystals in a unipack instead of 10. And they're easier to manipulate for the robots at the beamline, but they're more complicated for the scientists, especially because there is no vial around the loops. And so fishing and plunging in nitrogen can be quite tricky. Please be aware that different synchrotrons can accept different type of supports. For example, Diamond or Soleil can accept only unipacks. Here at the SRF, we have a mixed setup where we can accept both spine packs and unipacks, but this depends on the beamline. So every time you have an experiment, just verify before with the beamline scientists which kind of support can be accepted. Because transferring crystals from one system to another is very long, and it's a very, very big waste of time. And two, it's extremely dangerous because you will have to take crystals out of the nitrogen, which will surely lead to formation of ice. Let's suppose you have put your crystal in the adequate support. You need now to ship those to the beamlines. So the packs are put into dewars, more properly dry shippers, because you're generally not allowed to ship liquid nitrogen, but you can ship them in those dry shippers again. Why dry? Because they don't contain liquid nitrogen, but they can stay cold for multiple days at the temperature of liquid nitrogen. These are very delicate objects, so you need to take care of them. First, they don't need to be hit around, obviously. Mechanical shocks are very bad for them. They contain glass and a very sensible metal sponge inside. Also, you need to dry them properly. After a few usage, probably 2 usages, they will be full of ice coming from the humidity of the air when you mount the crystal. So the best thing is to let them dry completely before cooling them down again. Your crystal will then reach the beamline at some point. And at this moment, we can go through the actual setup of the beamline. So we have seen now how to perform the experiment, but what are the instruments that we use to perform this? The first is the diffractometer. You can see it here. On the diffractometer, what we have is a goniometer head where we mount the pins, and the pins are then rotated and put into the beam. So the diffractometer has 2 functions. The first is to position the crystal in front of the beam, and the second is to rotate the crystal very precisely. Why precisely? Because when we collect images with the detector, if we want to reconstruct the reciprocal space with precision, we need to know at which exact degree each diffraction image has been collected. Here is the detector. As you can see, the detector is mounted on a table. It can move back and forth to intercept higher or lower resolution. I repeat again, the farther we go, the lower the resolution, but the more separated the spots will be. The closer we get to the detector, the higher resolution we can collect, but we will have least separation between the spots, especially at low resolution. And then, as I said before, we need to keep the crystals at cryogenic temperature at all time, including the data collection. So we have here a cryocooler. This is an object that basically blows very cold air at 100 Kelvin to the crystal. And this is aligned with the crystal, obviously, to make sure that it doesn't shade the diffraction. And it keeps the crystal at cryo temperature of 100 Kelvin for the whole time of the experiment. Now, how do we handle crystals at this cold temperature? We use a sample changer for multiple reasons. The first is that, we don't want to touch crystals which are at negative 200 degrees for safety reasons, but also because with all the recent upgrades in beamlines in detector speed, goniometer speed, and the intensity of X-rays, the longer time of the experiment is actually the transfer of samples. Which is weird to say, but our limited time is the sample transfer. So if we put multiple packs inside the robot and then just let the robot mount the sample for us, we will gain a lot of time during the day. You can imagine that at the beamline, you can collect on average, without rushing too much, about 200 crystals per day. If you had to go in and out and do the safety procedure to enter the hatch 200 times, you would have wasted almost 3 hours of beam time just to do that. And another tool that you find at the Beamline is obviously the Beamline scientist. We are there to help you. So if you have doubts, we will take care of both of the equipment for you, but also don't hesitate when you have beam time to ask your Beamline scientist for advice. He knows the Beamline better than anyone else in general. So we have all these very nice automated things. We know how diffraction works. Now, how to collect data when we are at the Beamline, and we are getting closer to the conclusion. What we need to do is what is called a strategy determination. So before shooting X-rays to the crystal, without knowing anything, it's not a good idea to do that because, again, crystals can die due to radiation damage. So it's better to determine a few parameters before. But to optimize the data collection conditions, we need to determine at first space group and unit cell. This helps us in guessing how many reflections we need to collect so that we can get a complete data set. We need to determine the resolution so that we can position the detector at the good position. We need to determine the oscillation range, so how much degrees we rotate the crystal per single image, as we have shown before. We can estimate the expected lifetime due to radiation damage of the crystal, and we can guess the final quality of the process data. All of this is done from few, possibly one diffraction images. So here I will show an example of how we do at the SRF using the program BEST. As you can see, it's a very complicated system. Here what we did, here we collected 4 diffraction images to characterize the crystals, and we get a lot of indicators out. And most important, we get what we call a diffraction plan. As you can see here, resolution limit is set by the radiation damage. This means that the program can estimate how much radiation your crystal will stand to keep a reasonable resolution. This is done with this plot here. I will not go into details, but there are other parameters which are important. On the picture on the right here, we determine the oscillation range to avoid superimposition between the spot, which is important, as we have shown before, to determine the maximum oscillation that we can get. Is generally more than 1 degree. And on the first image here, due to the different symmetries and orientation is the crystal, it's important to also choose correctly the starting angle of the experiment. This is the minimal oscillation range. So this is the minimal number of images we need to collect, depending on the starting angle of the experiment. And you can see here, we can go for the same crystal. If we start at 0 degree, we need only 50 degrees of rotation. If we start at 50 degrees, we will need 80 degrees of total rotation to get a complete data set. All those parameters are obviously taken care automatically at the beamline, but it's been very important to follow them because X-rays at the beamline are very intense. So it's very difficult to come up with a good guess for what should be the exposure time, the resolution, and the oscillation range. So to summarize this quite dense presentation, take-home message. First and foremost, crystal diffraction allows to solve protein structure at the atomic level. Why this? Because the Bragg laws determines both how we set up an experiment, but also how much we can observe from our crystal. Most important thing to remember is that proteins are radiation sensitive, that radiation damage limits the achievable resolution, and crystals are precious and you have to take good care of them. So, because it's important to remember that you don't get a second chance to collect data from a crystal. In general, the first few images have already damaged the crystal, so your crystal will never be the same if you collect data twice from it. So I hope this was useful, and with this I come to the end of my presentation. I thank you for your attention. So,
thank you very much for the nice lecture, Gianluca, and I guess he's open to questions.
Yes, I will probably stop sharing my screen now. Voila. No, not this one. Sorry.
So maybe I can ask a question first.
Yes.
Thanks a lot for the presentation, Gianluca. So I was wondering, you mentioned that you at least need to have or collect data 180 degrees. I guess this is because most crystals have at least twofold symmetry, or is there another reason for this? And don't you also, if you have a P1 space group, need full 360 degrees or what?
Yeah, so in principle, yes, but there's one thing that you can consider is that there is what we call Friedel laws in crystal, which says that plus and minus HKL are actually equivalent. And this is true in all space group, which means in general, if you collect half of the data, you have a full data set. Okay, if the Friedel law is true.
Sure,
if you are in the experimental condition, which makes in sort that your Friedel law will be false, then you will need, obviously, as you said correctly, to collect 360 degrees.
Okay, thanks. Maybe I can ask a second question. So you also mentioned for the Ewald sphere illustration that in practice you actually have a bit of a larger span of energy. And I was wondering, does that in principle interfere with the X-ray interference? So if you have a completely monochromatic beam, would that in principle give you better interference between X-ray waves? If you understand my question.
Yeah, I do. So first, you need to consider that a completely monochromatic beam with no spread is an abstraction that cannot be made in practice. And so, yeah, but if we go to the abstraction, no, in the sense that the wavelengths are too close. And so in general, you will get diffraction at slightly different angles for the, how do you say, for the different wavelengths that you get inside. But when the spread is so small, at those wavelengths, actually the angle is more or less the same, let's say, size of your spot. So the error is negligible, I would say.
Okay, thanks a lot.
The answer was clear.
Yeah, sure, thanks.
I actually have a question. Given that we get radiation damage, if I would collect my first 30 images and then I would find out that I want to reconsider my strategy, can I just stop the collection, or is the damage going on while I think about it?
Oh, that's a good question. So at cryo temperature, you could stop and restart, and the dose you have put in will be slightly the same. Actually, those things move either quite fast or they don't move at all, the free radicals inside the crystal. So you could stop in time, but another thing you need to consider is that you can not stop in space either. So one thing, let's assume, for example, you have a big crystal. You collect for a while and then say, okay, I stop and then I want to collect from scratch. You could move to a new position and consider that your crystal has no damage in this position, but actually you need to consider that radiation damage, even at cryo temperature, would have spread a bit. So in general, it's safer to move about 100 microns away, but over time, the phenomena is more or less instantaneous. So it will stop at the moment you stop the collect. But if you restart, you need to consider again that, so you're stopped at image 40 and then you restart. The second start of your data collection cannot be considered as a zero dose image 0 or image 1. It will be image 41 for the level of radiation. So you always have to consider that. Sometimes it's negligible, especially if your exposure is quite low or quite conservative, I would say. Some other, it can make a huge difference.
And I have a question attached to that, and that is if I would take my images and then I would see problems, for example, overlapping spots or ice rings, what do I do then?
Oh, so for the ice rings, it depends. You cross your fingers and hope they're not there in all your crystals. No, just kidding. So for the ice rings, in general, it depends. There are two main sources of ice rings. One you can try to take care of. The other is a bit more tricky. If it's ice rings coming from, let's say, wrong manipulation in the lab, you can have the chance that your ice is just some ice deposit on the surface of the crystal. In this case, you can try different things. You could try to anneal your crystal for a second, which means you stop the cryostream, put it back in. At this moment, the ice around will melt. And you can try to refreeze the crystal after a second and cross your fingers that your crystal will survive. Or you could wash it. If you take some liquid nitrogen and just gently pour it over the crystal, it will wash away the ice over the surface. So if the ice is only over the surface, you can try at least this solution. Especially if you have not so many crystals, could be worth. Not so many crystals for a specific protein. Then if the ice again is due to, for example, bad freezing due to wrong cryoprotectant or things like that, you can always try to anneal. Again, annealing means stopping the cryostream for a few seconds and putting the cryostream back in. This can have three consequences in general. It can either change nothing, you can remove the ice rings and keep your diffraction correct, or it can destroy everything. So you can be finished with only ice rings in the end. But yeah, if it's your very precious crystal, it's worth to try. Voilà. We have a question actually you've seen in the chat.
Let me read it to you. What parameter allows us to observe radiation damage?
Okay, so the easiest thing that you can use to observe radiation damage is can look two ways, either the resolution or the intensity of the spots. Actually, the direct consequence is the intensity of the spots. The intensity of the spots goes down with the dose. Why I say consider the resolution? Because the higher the resolution, the weaker will be the diffraction spots. And so when the higher resolution spots disappear, this is because all the intensities have gone down by a center factor. And so it's not possible anymore to see the highest resolution ones, which are the weakest. So this is the easiest one. In post-processing, when you start to process your images, there are different indicators. For example, the Wilson B goes up. Wilson B goes up with those because of the, you can imagine that you're introducing some sort of thermal agitation inside your crystal that disrupts the order of your crystal. Or another parameter that you can observe is a bit tricky sometimes, but in general, this happens is that the unit cell volume also goes up with the dose. The higher the unit cell volume increase, the higher dose you put on your crystal, and so that's all signs of radiation damage.
There are more questions. Israel Maris says, thanks for the answer.
You're welcome.
There's a question by Jaga. How many minimum images are required to solve the crystal?
Oh, this is a tricky question. So probably you can go with the minimum oscillation range you can get, which is for a P6 space group. Actually, for a higher symmetry space group, you can need down to 27.5 degrees, if I'm not saying something wrong. But you can need less than 30 degrees anyway to get a complete data set due to the symmetry. Then how many minimum images is a bit more tricky because obviously you can go for a non-complete data set and still solve the structure. So if you're very lucky, you can go for 80% completeness, get your 20 degrees of rotation from your P6-5 crystal and just be happy with that. The number of images is also tricky because, again, as I showed you, you can change the oscillation range. So you can get for the same angle of data collection, you can change the oscillation per image. So you can do 30 degrees with 300 images, with 30, with 15. This also depends on other parameters that you can choose. So there's no real good answer to your question.
If I may add to this, most modern synchrotron sources allow you to shoot your crystal very strongly, and it may be a good idea to record even the same reflection several times as to lower the standard uncertainty, the experimental error on those reflections. So going for relatively good multiplicity of, say, about 3 or 4 is often better than shooting the crystal dead with a minimum amount of images. Also, a typical data collection on a modern beamline takes approximately 3 minutes, so that the number of images is often not a problem unless you're on a home source and it's a very popular home source. But synchrotrons, like for example, Diamond Light Source, allow outside users to send their crystals, and if the project is evaluated well, even at no cost often. So applying for beam time, if you have a valuable crystal at a good source with a good detector, may be worthwhile.
Yeah, just to add to what Andrea just said is, yeah, it's always in general better to collect a bit more images with, let's say, keeping the full dose constant, except, for example, why would you want to go to minimal images? You can have a metal center in your protein. The first image will destroy the oxidation state of your metal, the first diffraction image, so you want to get the least X-ray possible. This is one of the reasons why you would want to go extremely low dose of. If you're tracking a particularly specific chemical path where X-rays could actually disrupt the bonds that you're trying to create, that's a reason why you want to go to minimal images. So this will again give you worse, let's say a worse in general data set, but more precise to determine the structure you're actually interested in.
Then Rajiv wants to know, can we use 2 crystal data collected at different time point or different synchrotrons?
Okay, so I presume that the question is, can we merge them together to get a structure? In principle, yes, provided that you can determine one, that they are isomorphous. This is a very big domain, but in general, you need to determine that the crystals are, they represent the same protein in the same state. There are different ways to do this. First guess, you can look at the unit cell. If the unit cell is close enough, that's already a good hint. But then there is also another thing that you need to consider in all of this, which is the scaling problem. So different synchrotrons will have different detectors, different beams, different intensities. And so comparing the data between each other will be extremely tricky. So I would avoid that if possible. If not possible, you can give it a try, but yeah, it will be extremely tricky probably.
Any more questions? I have another remark, which is possible, very practical, but because I see a lot of students in the lab who are going on their first trip. Before you go on your first trip or you send away your first crystals, before you have beam time, you should consider making a plan. What is the, if you have only limited time, which crystals do you absolutely need to measure? What do you want to measure at which wavelength, which oscillation range, and which angular width for each image, given the detector at the beamline? And it's also good to have that plan ready when you encounter the beamline scientist, or if you're working with a home source, with whoever is in charge of that machine, and discuss that plan with them. Even who I have about 15 years or more experience in measuring data sets, always speak my measurement plan through with my beamline scientist. And I develop it days prior to the actual measurement, because at the beamline, you're under a lot of time pressure, and it may be 4 o'clock in the morning, and you may not do the wisest choices. And I don't say this because many of you are students, but because I have made unwise choices at beamlines myself. Are there any more questions?
Can I ask one more?
Yes, please.
Hi, Gianluca, and hi, Andrea. Thanks for this lecture series. And I'm calling from Australia. Yeah. The thing is, whenever I'm sending the crystals, like to the synchrotron in the Australian synchrotron, I do always have the radiation damage, particularly with one of my proteins. And it is very, very difficult for me to always like where to limit, where to stop, or what to do. As I tried to clear with the nitrogen, liquid nitrogen as well, and I'm still having those troubles. And I don't know what to do with the radiation damage. And adding to that, it is a particularly experimental thing. I don't know the crystallographers in the world get this problem or not. When I'm optimizing the crystals, like I get the crystals from the company conditions, but when I going to optimize, I didn't get it. And I'm using the fresh buffers, fresh everything, and I don't get it. And I send the crystals from the company things. I get the diffraction of 5 Armstrongs, but I try to do it like I have done it like at least 20 optimizations. I'm not getting the diffraction. I don't know why it is happening, or is this happen to everyone in the world, or it's only me?
So short answer is that it can happen, especially for the screening, and there's not much you can do. There's a lot of parameters that are very difficult to control when you do your experiment. As Andrea was mentioning in her first lecture, the people who use always the same buffer battle and not the other ones. There's some things that can change between what they use at the company and what you do, your pipetting skills, etc. So that's normal. In general, you just keep trying. And for me, for example, it was the production batch. I was using always the same exact condition during my thesis. Depending on the production batch of the protein, it will either form crystal which diffracted at 1.5 angstrom or not crystallize at all. Same condition, same everything. Voila. So this probably answered your question number 2. It's just fingers crossed and keep trying.
Okay.
And so it depends, because if you're seeing rings and you're washing your crystals, for the other part of the question, that's probably worth to screen through different cryo conditions. One thing you can do is that you don't waste crystals for this. If you have a home source, it's even better. Otherwise, you can just drop into a pack to the synchrotron. You just take your mother liquor, you mix with the cryoprotectant you want, you just freeze a drop of this and send it to the synchrotron. You shoot one image. If you don't see rings, that's already a good sign. So I would do that. If you obviously have a lab source at home, you don't waste a position in your shipment and just do that at home. But yeah, that's the easiest thing you can try if you're keeping getting ice. So screening through different cryoprotectants, you can change concentration, you can change kind, or you can go without changing for oil. So oils in general, what you do is that you take your crystal out, you envelope it in oil. So it's not a cryoprotectant like, for example, glycerol, which will replace water inside your solvent channels. It's more of a protection around your crystal that will screen it when you screen it from the cold, obviously, when you flash cool it. And so it will maybe give you better results. They're a bit tricky to manipulate if your tea crystals are delicate, but sometimes just worth to try.
Yeah, thanks. Thank you.
And good luck.
Yeah, thanks.
I also sent you a link in the chat for C0. So the C3 Crystallization Center are world specialists in cases like this, and they're in Australia. So it might be worthwhile for you to get in touch with them. And I mean, they will get a lot of questions like this. And I actually, when we have difficulties in crystallization, we sometimes discuss with them. If there are no more questions, you're all invited to spend the next half hour or so in the Telegram chat channel, where we are posting like more questions and stuff relating to this lecture series. And I would like to thank Gianluca again for his very nice lecture.
You're welcome. It was really nice to be here.
And I see you all back next week, same time, same place.